This is the 22nd episode of Advanced J1939 for Technicians. In this episode, I'll be looking at a John Deere S series combine that has some intermittent CAN issues. This machine's about 15 years old, so it has active termination on the machine CAN network. The machine CAN network is a 250K baud CAN network. Newer machines don't have active termination. They use passive termination, 120 ohm, and typically they're 500K. But this machine had a variety of issues that were very intermittent, very hard to duplicate. We were lucky to be able to capture this problem while the machine was out harvesting. We're able to quickly resolve the problem and get the customer back with minimal downtime. So as you can see here, the CAN trace of where I captured this issue, it looks pretty nasty. We can see that once again we have similar to the episode 21, it looks like part of the CAN network is working and some of it isn't. If I zoom in on this, I can see that I'm able to decode. This is a message from the engine controller. We can see that it looks good, but there's another controller or controllers that are obviously having issues. They're stepping on messages from other devices, which cause error frames. They're starting to transmit and interfering with those messages. Other instances, it appears that that device is continually retrying or trying to get on the CAN network, and then we can see really long error or really long acknowledge. This is really an error frame. The other devices are telling this controller, hey, we don't understand your message, stop communicating, please. So once again, I'm going to have to change the decoder because I'm using A-B, and A-B isn't going to get me anywhere when I look at a problem such as this. I can see that it looks like I've got one message that might have everything that I need. I really want the source address. I want to find out which controller or controllers are causing this problem. As I said, this was a very brief duration problem. I can't rely on diagnostic trouble codes. Once again, sometimes it sets DTCs. Other times we just have complaints of, such as engine speed dips momentarily. I may or may not set DTCs, and if I do, they're not always the same messages indicating the same controllers are missing or that there's problems with those controllers. So just like in the last episode, I'm going to have to modify the math channels. So I'm going to go ahead and look at this math channel. It's not going to do me any good. I'm going to use instead. So I had Picoscope crash on me. I had to restart it, but here we go. What I did was I changed the math channels. I went from A-B. I created a math channel called A-2.5. because that looks like that's going to get me something that is going to be close to 0 to 1 volts that I can actually use to decode. So I put that into the decoder. I used the A-2.5, set my thresholds and my hysteresis, and looks like here I'm able to decode at least this message from this controller. So zooming in on this, we can see that this is source address F3, and F3 in hexadecimal is 243 decimal. Looking at the display on the machine or information that John Deere might be able to provide for me, hopefully, I can find that source address 243 is a controller called the RC1 controller. It's a harvest controller that's on the combine, does some stuff related to the combine. I don't know, I'm an engine guy. So I'm going to go ahead and zoom out a little bit here, and we'll take a look to see if we can see it again. And we can see that I don't know that I have another instance of that 243 being present someplace that I can find it, or F3. But if I go through all these waveforms, I'm sure that I would find someplace. Looks like here I have the 243. I'm able to actually get that message through. We can see that there was error frames from some device. Some device did not believe or did not acknowledge or like what it saw. One or more controllers, so we ended up with an error frame because of this. So one of the things I guess I wanted to point out in this, the actual problem with this is I had an intermittent open circuit on CAN low at that controller. So I had a terminal that's loose at that controller, a female terminal that was loose, and so it was a very intermittent issue that it was causing. We can see here this has active termination. In my last video, I had a machine that had an intermittent, very high resistance or almost an open circuit, and it caused CAN high to follow can low. In this case, and my problem with that machine was can high. In this case, my problem is with can low. And you can see that can high looks good in the yellow. What looks questionable is can low. Can low is staying close to 2.5 volts. This is one of the differences that you'll see with active termination versus passive termination. So the active terminator is going to try to hold the CAN bus at 2.5 volts. So instead of having a path where the CAN low or the CAN high can kind of sneak back through a resistor, instead this is going to hold it. So this is one of the differences that you're going to find if you are rigging on a machine with active termination. A lot of ag machines, the implement bus, or probably almost everything, the implement bus is active termination. I think newer machines, I don't know that anything on the vehicle network anymore is active termination. They pretty much went away and went to passive termination. You can ask John Deere why they did that. I'm not going to answer for them, but anyways, you can see with active termination, it definitely changes the waveform. So I'm going to go ahead and go through some theory that's going to help explain this phenomena that occurs whenever I have either can high or can low open someplace on the network, whether it's at one single controller or whether it's on someplace where we call the backbone. So if it's at one controller, in the case like the combine that I just showed you, I'm only going to have problems with that one controller, and I can isolate it down to typically it's either inside of that device or it's at someplace in what we call the stub, the connection between the controller and the backbone. So someplace there we have the open or the very high resistance. So in this case, what I have is I've modeled a CAN network that has two passive terminators, so 120 ohms at either end. I have six what I'll call controllers, and then I've introduced a couple of places here where I can open can high and can low. So this is can high up here at the top. This is can low down here at the bottom. I'm going to go ahead and run a quick simulation on this, and what I'm going to do is I'm going to have this controller go to a dominant bit for 2 microseconds, then it's going to shut off, and then this controller will transmit a dominant bit for 2 microseconds. So if we go ahead and go through the simulation, this will be a total of 20 microseconds. So we'll run the simulation, and there we can see on the CAN bus it looks similar to our oscilloscope where we don't have any problems. So this is the controller that's on the right side. It's transmitting 1 bit, 2 microseconds. We go back down to a dominant bit, then we go back down to a recessive bit, and then the other controller on the left side, it's transmitting. So it's like, okay, this looks like our CAN bus. So blue is CAN high, the orange is CAN low. We're centered here on about 2.5 volts, as we'd expect. Okay, so now what I'm going to do is I'm going to introduce a failure mode here. I'm going to go ahead and open CAN low at this point. So we have our switch. I'm going to open this. This gives us an open circuit on CAN low. This could be an open. This is going to be an open in the backbone. So these two controllers are still going to see each other fine. The network's going to basically split up into 2 separate networks. I have a terminator here and I have the other terminator. So we're going to first watch from the perspective of this where it says CAN high 2 and CAN low 2. So I'm going to watch as though my scope is connected to this right side, and we'll see what the simulation looks like. So I'll go ahead and simulate. I'm watching that expression. We'll go ahead and run, and we can see that when the device on the right side communicated a dominant bit, our CAN pattern looks normal. I don't see any issue with that. However, looking at this from the perspective of the right side, when the left side controller tried to communicate a dominant bit, CAN low follows CAN high, and it traces perfectly with it. The great thing with our simulation here is I don't have any capacitance or inductance that would be present in a real wire harness in the real system. I don't have those elements here, so I don't see the overshoot, undershoot, oscillations, the kind of noise, I guess you would call it, that I see on the other CAN bus. Okay, I'm going to go ahead and simulate again, but this time I'm going to watch from this left side. So I'm going to watch from the terminating resistor that's on the left side of the circuit. So my problem is down here on the right. There's my open switch. This controller is going to transmit first, and then this controller is going to transmit a dominant bit. So we'll go ahead and modify the simulator. We'll go ahead and take these two off. We're going to add an expression. We'll get this one, and we're going to get this one. So we have VCAN high 1 and VCAN low 1. We're going to watch those this time. It's the same simulation, but as we can see, it's now flipped. So from the perspective of watching this on the left side, this depends on where you hook up your oscilloscope. Where are you at on the network relative to where the failure is? This time, it looks like I have a problem with the controller that's on the right when it transmits a dominant bit, but the controller on the left, when it transmits a dominant bit, it looks perfectly fine. Once again, we don't have capacitance and inductance in this, so we don't have the ringing and the oscillations and things that look like on the real network. Okay, I'll go ahead and change things. This time I'm going to change the failure so that it is an open on CAN high instead of CAN low. So we're going to go ahead and open CAN high. And when I go ahead and open it and we run the simulation, we'll just watch from the perspective of the left side. We know what it's going to do on the right. We'll go ahead and simulate. We'll run our time domain simulation, and there we go. So what I have here for the controller that's on the right, when it transmits a dominant bit, from the perspective of the left side, where I'm watching it, when that right side controller transmits its dominant bit, CAN high follows CAN low. And it's because of that terminating resistor. All of that current is going through it. It's not able to build any voltage on the other side. So we'll look and see why that is. But the device on the right side, it looks fine. Everything looks good. So what's happening is, because this is open and I'm watching it from that left side, I cannot see whenever watching it from the left side, I cannot see when this controller drives CAN high to pull up through this 5 volts. It's not able to detect that. So instead, whatever happens with CAN low gets mirrored around and it sees it on CAN high at that input. So because of this terminating resistor, it causes CAN high and CAN low to look almost identical, other than the drop on the voltage on the wire harness, the impedance of the wire harness. Okay, so here I've modified this network. It's the same network. The only thing I've changed is I've removed the passive 120 ohm terminators and I've replaced them with a very simple terminating bias circuit, so an active terminator. This is basically just a couple of 2.5 volt regulators so this one holds CAN high at 2.5 volts. This one holds CAN low. There's a series resistance here of some value that allows there to be differences in voltage between this side and this side. Otherwise, that voltage would have to be held at 2.5 volts, and we don't want to do that all the time. We need a resistance there to allow there to be a difference in voltage. So looking at the other side, we can see the active terminator, if you would, what's called the active terminator, or named the active terminator, I'll just call it that, is supplied with battery and ground. This may be something from key switch, or it may be something that's generated by the machine, whichever. But regardless, that battery power and ground on active termination goes to the other identical part number terminator that does exactly the same thing, other than it doesn't have a jumper between 2 pins in the harness. It doesn't provide that. But anyways, this battery power and ground does the same thing in this other active terminator. So here's my other terminating bias circuit. So I've replaced the terminator. So once again, I've got an open circuit on CAN high, and I'm going to watch from the perspective of this left side. I'll go ahead and simulate, same simulation. And the difference that you're going to see here is when that right side controller tries to broadcast a dominant bit, instead of following CAN low, that open circuit, the terminating bias circuit on the left side has held what I see on the left side at 2.5 volts. So this is why when I look at this, I see that because this has active termination, we're held close to, that's not exactly, but it's like 2.75 volts. It's close to that 2.5 volts. It's holding it there, whereas if this were passively terminated and I had this same failure, the CAN low would follow CAN high. And there is a lot more distortion when that occurs, as you saw with the previous video with passive termination. This is one of the advantages of active termination. Some of these messages might actually get through by using A minus B. There may be enough voltage there that I get some messages through, and that's the case with this machine. Some messages were getting through. If it were passively terminated, it would have been a slightly different story. So if I were to change and open the other, we'll go ahead and do that just to prove that it works. We'll go over here and we'll change the failure mode so that it is an open on can low instead of can high. This is a lot easier than doing this on a real machine. So there's our failure mode, and we'll go ahead and simulate again. Let's see what we get. And there we go again, same kind of thing. So in this case, can high is there and present when the controller on the right side transmits a dominant bit, but can low is held at 2.5 volts. If I were to go ahead and do this, if I were to watch instead the other side, I'm going to instead watch over here. I do need to put a couple of nodes in. We'll do a couple of nodes. Let's call it right high, and we'll call it left high, right high, or right low, left low. So we'll go ahead and simulate. And in this case, I'm going to get rid of those two, and I'm going to add these expressions. And we'll run our time domain, and there you go. It's the same thing. So now I move my scope down on the other end. When the controller on the right has a dominant bit, it looks good, but it makes it look like our problem was with the controller on the left. So this is something that could probably get very confusing, but if we just try to think through what's happening and what's occurring, maybe we'll be able to get lucky, and as in this case, able to find a place where I'm able to decode the controller that's causing my problem, or in this case, the wiring issue that was causing our problem, not even the controller. So a very inexpensive fix, other than, of course, the labor and the travel and the time it takes to find this, but really no parts other than terminals to be replaced in this case.